So hi everyone. Today we will be discussing about how can you run LLMs in less GPU and CPU memory. So basically there are different methods like quantization, half precision, safe tensor GGUF file format, device and memory mapping, attention slicing and CPU offloading that you can implement to optimize on memory as well as on latency. So let's get started. So basically, if you would be knowing, LLMs are large language models and they are huge in size, which requires at times few minutes, that too when using GPU for even inferencing. So forget about training. But GPU is not that easily accessible to everyone, right? So how should one explore and experiment with these LLMs? So there are certain optimization techniques that we would be discussing in this particular video, and then you can implement it quite easily. So the first one is the most common one, that is quantization. So if I talk about quantization, in quantization, what happens is basically in ML models, what we do, all the weights that we have for the model are usually stored in a float 32-bit precision. That means each weight takes 32 bits in the memory. Now, quantization means that we are reducing this memory to a lower precision, be it 16 or 8 bits or 4 bits. So, this can be very, very handy. Just assume that you are reducing the size by half or at times by 4 cross if you're reducing the bit size to 8 bits. So quantization can really help you in reducing the memory requirements and can load the model quite easily. Also, it has been found that for quantization, the accuracy hit that is taken, the results is not that great. So usually the performance remains almost the same, but with one fourth the size. So that's the best part. Now we will be discussing about different quantization methods. So the most common one is the 16-bit variant, which is also called as half precision model. So how to load quantized or half precision model? So the first one is, if you go on Hugging Face, I will be showing you a screenshot. There are certain quantized version of these models. If you want to load these models, eventually these are straight away quantized for you. So if you see in this screenshot 8-bit, here you can see that 8-bit variant of Llama 3.2, Quen 2.5 coder 8-bit. Hence these are already quantized for you and they are uploaded on Hugging Face, so you can load them easily. Second, here is the code that you can use for loading. Very straightforward, nothing much to do. If you have used local LLMs from Hugging Face using transformers, you require an auto tokenizer and auto model for causal LLM, and then load the model straight away. Nothing much. The second method is a very exciting library released, that is Bits and Bytes, that you might have heard as well. Is a lightweight Python library designed to optimize performance of ML models by providing efficient implementation of quantization. So here you can mention which quantization you wish. So here you can see that we are mentioning this particular config, quantization config, load in 8-bit, load in 16-bit equals to true. And while loading for auto model for causal LM, you need to mention this quantization config here. This is the only add-on and rest of the things remains the same. The third method is loading the half precision method using torch. So here also you just need to mention one parameter while calling the auto model for causal LM, that is torch d type equals to torch.float16, setting the model to use float.16. That's it. So this is our three ways in which you can load the quantized version. I think you have used transformers before, so these are minor adjustments to this particular code. Now moving on to the next method, that is SafeTensors. So you might be hearing that if you go into the model repo of some of the most popular LLMs, you might be seeing that they have a separate file called as SafeTensors. So it is a file format in which the models are getting stored, which is more efficient and safe as well. Now talking about certain advantages: efficient storage, compresses tensor data to reduce memory and disk space usage. Data integrity ensures safety, faster loading, cross-framework compatibility, can be loaded using PyTorch, TensorFlow, JAX, secure tensor handling, and scalable. Now, how to use safe tensors? So first of all, you need to make sure that in Hugging Face or on the model repo, there is a .safe tensor file and there is a safe tensor.index.json as well. These are two files that are required. If it already exists, then you don't need to do anything. In the previous code where we were adding parameters, you need to add a one more parameter, use underscore safe tensors equals to true. That's it. So while loading from pre-trained, use safe tensors equals to true. That should work for you. Now moving on to the third one, that is GGUF. So if you have used Comfy UI, so there you might be seeing that a lot of people are talking about the GGUF format. So it is also a type of file format for storing and representing LLMs, which focuses on flexibility, efficiency, and portability. Efficient storage, faster inferencing, cross-platform supports quantization. So GGF format is quite trending now, and similar to 8-bit search, just go to Hugging Face and search for GGUF. So you would be finding the GGUF version of the most popular LLMs there present. Now this is a tricky part because using GGUF is not as simple as using safe tensors. So for that, I have figured out a way that using Olama and Python, you can do it. So basically, Olama has started supporting GGF format. The video is already covered on the channel, so you can check that out. How you can load the GGF file format into Python. And there is one more method called as Llama CPP Python. So you need to pip install this particular package and then mention the location of the model. This is GGUF, and then just start using it. This is the code snippet. You can find the blog on the internet. Now, once we are done with GGUF, the next methods are device and memory mapping. I think this is the most important one because device and memory mapping, when loading LLM, refers to how model parameters, be it the weights, activation, gradients, are assigned to manage across various hardwares that are present: CPU, GPU, specialized accelerator. So we will be first discussing the device mapping. Device mapping involves deciding where each part of the model will reside. So the common devices are CPU, GPU, TPU, edge devices that you might be knowing. Different strategies can be used for device mapping, like data parallelism, splitting the data across devices, or model parallelism, dividing the model itself. For example, during model parallelism, one part of the network can be placed on one GPU and the remaining on other GPU. Similarly, for memory mapping, involves mapping model weights and parameters directly into VRAM. If you have heard of it, allows efficient access to model data without loading everything into RAM at once. So, if you have heard of models like ChatGPT, for example, GPT-3, which uses GPT-3 or GPT-4, they have billions of parameters of data. So the model size is about 170 or 180 billion parameters. I remember for GPT 3.5, which is humongous. You require lots and lots of memory, which is not possible to load, right? So in that case, memory mapping can be a great thing. There are different strategies for memory mapping as well. Gradient checkpointing, storing only a subset of intermediate activations, pruning, removing unnecessary and redundant weights, mixed precision, loading some weights in precision 32 bits and others in 16 or some in int 8. So you're using a mix of, you're not setting up precision the same for every weight. This is called as mixed precision. How to use device mapping? So here you can see that again, auto model for causal LM. From pre-trained, there is a parameter device map, which is auto usually automatically distributes. So there are three parameters for it, three values that you can try out. Balanced distributes layers evenly across devices. Sequential loads layers sequentially onto devices, and auto is by default. How to use memory mapping? So there are multiple methods of memory mapping, as we saw: gradient checkpointing, pruning, mixed precision. So in this example, I'm showing you how you can go with a popular method called as CPU offloading. So in CPU offloading, it refers to moving certain part of the model computation from GPU to CPU. Right. So you won't be having all the memory available just as GPU, right? So you would wish to use your CPU as well. So this is called as CPU offloading. So CPU offloading can be done using this particular line, model dot to CPU. Move the model to CPU initially. Now you might be getting a little confused between device mapping and memory mapping. So just to clarify, so device mapping refers to assignment of tasks to different hardware, CPU, GPU, TPU, right? While memory mapping deals with how and where data is stored in memory of those devices. The goal is to allocate models, weights, and intermediate results in the most efficient memory space, CPU RAM or GPU VRAM, toward running out of space. Now, coming to the last one, that is attention slicing. It can also be taken as a memory mapping method only, where what we are doing, we are breaking the attention calculation into smaller chunks. So if you know attention is all you need paper, the dimensions of the attention metrics are huge, right? So for example, if the model is handling 512 tokens, it can process them into four smaller chunks of 128 tokens each. So we are trying to break down that attention matrix that we have, right? By slicing the attention matrix, model can maintain a lower memory footprint, and large models now can run on lesser GPU compared to what they are running with a default implementation. Now, talking about attention slicing implementation, right now Transformers library don't support it. So it is supported by just diffusers. Diffusers is basically for image generation. So how to enable it? Nothing. You need to load the diffusion pipeline, as you can see, very similar to Transformers only, and then pipeline enable attention slicing. That's it. So as you saw in most of the code, in most of the optimization technique, you just need to add one line or one parameter, and by this you can run your LLMs, optimize it for limited hardwares, right? I hope you try these methods out and you are able to run the LLM of your wish on your local system as well. So, by summarizing the video, we talked about a number of optimization methods here, starting off with quantization. Then, half precision is a type of quantization. SafeTensors and GGUF are specialized file formats. Device mapping and memory mapping. CPU offloading is type of memory mapping, and then attention slicing. I hope this was useful and you try these methods out. Thank you.